Good evening, everyone. On behalf of the Electrical Engineering Society of the University of Moratuwa, I warmly welcome all of you today for this insightful educational session. We are truly honored to have with us Engineer Saumya Kumaravadu, the Project Director of the Power System Strengthening and Renewable Energy Integration Project at the Ceylon Electricity Board. With years of experience in the energy sector, Engineer Kumaravadu has contributed extensively to power system planning, renewable energy integration, and grid modernization. He plays a key role in driving Sri Lanka towards its ambitious target of 70% renewable energy by 2030, while also addressing the vital challenges of reliability, affordability, and sustainability. Today, he will share his valuable insights on tracking the sunny Sunday effect and the future of renewable energy in Sri Lanka. Without further ado, it is my pleasure to hand over the session to our esteemed guest, Speaker Engineer Saumya Kumaravadu.
Right. Thank you very much. Can you see my cursor here? You can. So I'm sharing. So give me a second. I will share my. Can you see my slides?
Yes, sir.
Right. So I have to minimize this, I think. Yeah. Right. Can you see my cursor? So moving here, that I think.
Yes, sir. Yes.
Yeah. Right. Fine. So you all can hear me. I think you can see my slides as well. So if there is problem, so let me know, please. Right. First of all, I must thank to the Executive Committee of Electrical Engineering Society of University of Moratuwa, especially to the President of ISOC, Dr. Asara, and Vice President Sasindu, who contacted me, and also the young engineer who passed out from University of Moratuwa, Engineer Power, for inviting me for this webinar and also selecting me as the resource person. Today our topic is navigating sunny Sundays for a sustainable, reliable, and affordable electricity future. It is a broader topic where this topic is navigating sunny Sundays for sustainable, reliable, and affordable electricity future. Because of it is a broader topic, so I will use a considerable number of slides here. And also, I use a few slides to give you some idea about the basics of and principles of power system operations. And then I will switch to the main topic. Right, because of actually, so I give a brief idea about the principles of power system operation. I know the students in different levels are participating here. So easy understanding of my topic. So you should have some idea about the basics of power system operations. Let's move to my slides. About few months back, there was a total blackout in Sri Lanka. It's an island-wide power failure. There were a lot of news saying that total blackout was triggered by a monkey. It is funny anyway, but that was the truth. So that was whether this problem still prevailed or that problem has been solved. And also people wonder whether a monkey can trip a national grid of a country. Right, next slide. This is the generation curve of a working day. So in the generation curve, you can see in different colors the energy mix of different which contributed in a working day. So x-axis give 24 hours. This is active power. So you can see there's a morning peak and evening peak between 6 o'clock to about 10 o'clock in the evening. And you can see the minimum power generation or load is at about 12 noon in the daytime. Can you see my cursor?
Yes, sir.
Right,
We
fine.
can see.
So you can see the minimum load is about 1500 megawatt in the x-axis. But this is not the actual generation. Actually, this is what the transmission network see as the generation curve. And also, this is what the system operator see as the generation or demand curve of that particular day. This is a weekday. So next, this slide. So this is the generation curve of Sunday. It's a generation curve of Sunday in month of June. So that particular day, a total blackout was happened. It was a Sunday, a sunny Sunday. The generation curve is same as this. It is same. So you can see the difference between the previous one and this one. So minimum value of generation at about 12 noon, it is about 1500 here. The next one you can see it has dropped to about 800 megawatts. So you can see a deep valley here. So this is the generation curve of a sunny Sunday. And in that particular day, the shape of the generation curve and share of power generation by different resources here were same. Right, let's see how this created the total blackout, how a monkey can trip the power grid. So why this power system was that unreliable. Next one, this is the duck curve. This is a very interesting curve. You see, this show the power generation curves of last 5 years in Sundays. The topmost curve, the blue colored one, is a Sunday in year 2020. You can see the minimum value in this curve around 12 noon, that was about 1500 megawatt in the y-axis. So next one below blue one is a Sunday in 2021. And next one is 22, 23, 24. And the bottommost one, the green colored one, is a Sunday. That is the Sunday, 9th March 2025. In last Sunday also, a few days back, the power generation curve is like this, right? You can see in the topmost one, about 5 years back, the minimum load is about 1500, 1600, but it has dropped to about 800 megawatt in this year. So this is the basic reason for the sunny Sunday effect and the system becoming unreliable, reliability goes down. So we will discuss in detail so how this happened, right? So let's move to my next slide. So you should have how the supply and demand of a power system is done. So supply demand balancing of a power system is simply explained by this picture. You can see he's trying to maintain a constant frequency. So maintain 50 hertz frequency. If the frequency is 50 hertz, the left side and right side is balanced. That means the power load, the power consumption, or we can say the demand and the supply is balanced. This 50 hertz frequency is a unique one in all over the country. If the frequency in your home is 50 hertz, that is same in everywhere. In Victoria Power Plant, in Kotmale, or in anywhere, the frequency is unique. So when the consumption is more, the demand is more, so left side goes down, then the frequency goes down. What system control center do is he add some generation to the right side, right? So likewise, if demand goes up, goes down, then they have to reduce the generation. And there are some limits in frequency if this and lower side and upper side, both sides, if that level is exceeded, So the under frequency or low frequency alarm comes. So if that frequency level in the under frequency side or frequency side will go beyond some level, say if in lower side, if it go beyond 48 hertz or 47.5 hertz, or in the upper side, if it go beyond 52 hertz, some equipments at 52.5 hertz, then the generators and feeders and some equipments connected to the system will be tripped because of under frequency or low frequency. And that will cause to a cascaded effect, and that will initiate total failure or partial failure. So my next slide. So these three elements, the techniques are used to balance the supply and demand. These are the global norms, not only Sri Lanka. So inertia and kinetic energy, then primary regulation and secondary regulation. We use some other techniques like load shedding, so in some emergency cases. But in automatically, when the system is supply-demand balancing is done in automatically, so these three elements are used. So let's see what is inertia. You know that what is mechanical inertia. So in mechanical systems, we flywheels. So what is the role of the flywheel is when it is rotating, the flywheel has stored kinetic energy. When the system, the mechanical system speed goes down, that stored mechanical inertia, the kinetic inertia of flywheel is released to maintain a constant speed. Likewise, it can absorb or it can release its stored kinetic energy to maintain a constant power and speed. Similar to that, in rotating generators, but if I can move this little, so let's keep here. So similar to that, so in rotating generators, there are heavy rotating parts like generator rotor shaft, turbines, and in thermal power plants, some compressors like huge components are rotating. Those rotating parts are similar to the flywheels. So those have stored kinetic energy, and they support to maintain a constant speed in this particular machine. If consider, because of some reason, the system frequency goes down. The system frequency is proportional to the speed of the generator, synchronous generator. When frequency goes down, generator speed also going down. Then this machine's inertia support to maintain a constant speed. That means ultimately the machine's inertia support to maintain the frequency of the machine and to support to maintain the frequency of the system as well. Then inertia of all rotating machines in the system together support to maintain the system frequency at 50. That is the inertia support of rotating generators. If I can move a little. So my next slide. So this is a very important parameter, inertia constant. So inertia of a generator of a system is given by this inertia constant. Inertia constant is the kinetic energy stored by that particular rotating generator divided by its rated apparent power. So that is a energy divided by power, then a constant is a time. So energy divided by power means it's times. Generally, a constant of machines or the system is given in seconds. So by this equation, the total H constant of the system. So we say system inertia is given by this equation. So you can easily understand what is this. This is the S of a particular, the apparent power of a particular machine, this H constant of that particular machine. And this summation, the equation is given, gives the total inertia of the system. Next, these two curves compare the frequency response of different systems having different inertia levels. So red one gives the frequency response in the contingency a system with high inertia. The dotted line is the frequency response of a system with low inertia. You can see the frequency drop in high inertia system is lower than the other one. You can see the initially in the contingency, initially the inertia, the support come first, and then there is a technical primary regulation and then secondary regulation. By inertia, primary regulation and secondary regulation, this frequency will bring down to the normal value, 50 Hertz. So that is inertia. Then let's see what is primary regulation. I said three components we used to mainly used to supply demand balancing. In primary regulation, there are governors in rotating generators, synchronous generators. The governor has different functions. So it has a group setting and it controls the power, and there are load control mode and isochronous mode and different modes. But one function of a particular machine, one function of a governor of a particular machine is maintaining the speed. So it get the feedback of if actual speed, there's a reference value of speed, that is the rated speed of that particular machine. If there is an error, speed error here, this governor gives a control message to open the wicket gates in case of a hydropower plant, or so open the fuel nozzles to give more fuel or reduce more fuel, depending on this error, the plus error or minus error, to maintain the speed of that generator. So all the generators connected to the system together, the governors of all the generators, the rotating generators, synchronous generators together support to maintain a constant speed, constant frequency of the system. That is primary regulation. Right. Then secondary regulation. Second regulation is the frequency control of power system. For frequency control, we use large generators having fast responding ability. Generally in Sri Lanka, we use large hydro machines, and we can use the gas turbines as well. So let's see, we use the machines with these generators, large hydro generators, and the sixth one is the generator, the gas turbine of combined cycle power plant in Kalmytissa also can use to frequency control in purpose. So let's see what is frequency control, how it is done. Assume in a particular time, the frequency control is done by a single machine of Kotmale power plant. The capacity of a single unit of Kotmale power plant is 67 megawatts. Generally, the group setting of other generators are set to 4% speed group setting, 4 or higher. But in the frequency control machine, group setting is set to 2%. That means that I think you can see, so I am not going to teach you what is group setting and etc. So what is that characteristic is, if the group setting is set to 2%, this power plant can go in full span of its capacity. That means it can move from 0 megawatts to 67 megawatts for a 1 hertz frequency deviation. So this is quick. So generally we use quick responding and large generators for frequency control purpose. So think in a particular time in this load curves, see after the morning peak, so the load will be increased gradually. See, think that load is increasing gradually. And when load is increasing, the frequency goes down, then when it is happening gradually, that's Kotmale power plant, general frequency control machines is kept at the middle point so that it can go to lower side or upper side. If frequency goes down, that means we need more generation, then this Kotmale power plant will increase its generation gradually to some value. Then the frequency will be balanced. So that's the frequency controlling. We call it secondary regulation. This curve gives you how the inertia control and primary regulation is happened. But this is a simulation, and this is not the actual curve, frequency response curve of a system. That is not this beautiful and this like smooth like this, smoother like this. It is a different one, but I use this simulation to just explain you the principle. So you can see the inertia gives support to maintain some frequency in some level. Then the primary regulation, the governing systems connected to the system together correct the frequency and bring the frequency for a particular level, but still there's a frequency error. Then frequency control machine, the second regulation, bring the frequency to the normal frequency. So that's how those three components are used, help to keep constant frequency and to help to supply and demand balance. Right. Next, when you talk about sunny Sunday effect, so our main topic is navigating sunny Sundays. So when you talk about sunny Sunday effect and the reliability of the system, so renewable energy become a main subtopic. So why do we need renewable energies? There is a threat in the earth that increase in of greenhouse gases like carbon dioxide. So because of that reason, increase of CO2 like gases, as a result, ocean acidification, global warming, retreat in the glaciers, and rising sea level like effects are talking about. So these are some measurements at Mauna Loa Observatory. It is a reputed research facility in Hawaii Island in US. So this show some values in past years, how this global warming and the rising of sea levels happened. To mitigate those climate changes, going for renewable energies is crucial. So we should go for renewable energies. The solutions for these are renewable energies, and we are talking about some emerging technologies like hydrogen fuels and hydrogen cells. So we generally call green hydrogen. And also, the conventional energy resources are depleting with time. One day, the coal and all fossil fuels, fuel oils and everything will be finished. Then we have to go for renewable energies and green hydrogen like emerging technologies. It is obvious. When you talk about renewable energies, very important renewable energy source is major hydropower plant, because large hydropower plant has inertia and they are firm energy power plants. They are dispatchable power plants. But when we talk about our country, the most of hydro resources are already utilized. Because of that, the future all RE additions will be new renewable energies. So we call wind and solar new renewable energies, right? There are some other non-conventional renewable energy sources, but wind and solar are the major resources we have to use. Right. When we switch to variable renewable energies, we have some challenges. We can categorize these challenges into two main categories. One is technical challenges, other one, the non-technical challenges. So we'll talk about these technical challenges. There are a lot of technical challenges, well, but I talk about only three challenges here, main three challenges. And we talk about the solutions as well. There are solutions for technical challenges. Everything can be solved, non-technical challenges in my next slides.